Alrighty now, let me just go ahead and share. Okay. So, all right, so this is gonna be what is this? Physics 315. We're gonna be talking about chapter 8, which is gonna be your torque. Okay, so supposedly, let's say I got a ruler. So I got a ruler right over here. And I don't know, put like a little nail. Actually, let me draw a better ruler than that. That looks a little better. Let's say in the middle of it, I go ahead and put a little nail. Now, what would happen if I apply a force this way? Well, it will go rotate on that way. All right, what would happen if I apply a force this way? It will rotate on that way. So let's say this is our ruler. Maybe I should go ahead. So this is our ruler. So when you apply a force on a ruler, let's say you have a nail in there, the ruler will rotate in that direction that you're going to put a force on. You put a force on over here, it's going to rotate in this one. That's what we talk about torque. And the best definition is what causes an object to have angular acceleration. Now, your torque, we're going to give it a letter tau. That's going to be your torque. And it's going to equal to your force times your distance, which is going to be your force is going to be in newtons. Your distance is going to be meters, so it's going to be your Newton meters. Let me go ahead and write this down. So your torque is going to be your force times your distance. Let me go. I didn't label these over here. Let me go ahead and label this. So this is your force in newtons, and this is your displacement. Or this, which is going to be your delta x, which is your x final minus x initial, which is going to be your final position. This is going to be your initial position. So your torque equals your force over this. So let's go back to our ruler example. Let's say we have another ruler right over here. Boom. And let's say I'm going to put the nail on it right over there. And let's say I put a force. Say I put a force right over here. This force is going to be at 5 newtons at a distance of 10 meters. And let's say I got this distance right over here is 5 meters. Where I'm putting a force over here. Now let's find out how much is this force. So you got a force going on here. So obviously that means this will rotate this way, which is going to be counterclockwise. And this force is going to be about 10 meters from the pivot, where the other force that we're actually putting in is 5 meters. We need to find out how much is the other force. Now, in order for, well, before we start, solve this, we need to do something. So I'm going to write it right over here. Now, your torque is positive if it goes counterclockwise, and your torque is negative when you go clockwise. What does that mean? Okay, so we got this example over here. We have a ruler again. You got your force at 10 meters. You got you got another force at 5 meters. This force is 5 meters. Now, in order for it to be in equilibrium, that means all our forces has to equal to zero. What does that mean? That means all our forces in the x direction has to equal to zero, and all our forces in the y direction has to equal to zero. All right. Which means that all our torque forces has to equal to zero. All right, now we have two types of torques, one and two. All right, which means that your first torque is going to be torque one plus torque two. Let's say this is F1. Find this as F1. Let's say this is defined as F2. So the distance one. So be the torque one plus torque two. That's going to have to equal to zero, which means, so for this one, your torque one is going to equal to what? Your force times your distance. In this case, our force is 5 and our distance is 10. So it'll be 5 times 10, which equals to 50 Newton meters. Now, so let me go ahead and write this one down. So this is going to be your 50 for torque one plus, and we need to find out what torque two is. Get a different color. For torque two, now this is going to be going over there. That means it's going to go this way, which means it's going clockwise. So your torque is going to be negative. So it'd be minus your force times your distance. And in this case, it'd be minus F2 times your distance 5. So over here, I'm going to go ahead. It is going to be minus F2 times 5. That's going to equal to 0, which means that solving for this, 50 minus 5 F2 is going to equal to 0, which means that F is going to equal to maybe 50 divided by 5. We're talking about 10 newtons. So technically, the torque over here, we get the same color, green. So your torque 2 is going to equal to minus 10 times 5, which is going to be minus 50 Newton meters. That is awesome. So the torque is what causes an object to have an angular acceleration. Now, let's look at the word angular acceleration. Now, your angular acceleration, you're going to give it the letter alpha. So in order for a body to be in equilibrium, all your acceleration in the x direction has to equal to all your acceleration in the y direction, which is also in the z direction is going to equal to zero. Same thing. All your rotational acceleration alpha is going to have equal to zero, which means this one, that means all your summation of the forces in the x-axis has to equal to zero. All your summation in the forces in the y-axis has to equal to zero. And which means that all your torque summation is going to equal to zero. So in pure translation motion, all points on an object travel on a parallel path. The most general motion is a combination translation of rotation. Now, what causes an object to have an angular acceleration? Torque. And the amount of torque depends on where and in what direction the force is applied. And again, if the force was applied and you have a rotation going clockwise, your torque is going to be positive. And if you're going to go, sorry, it's going to go counterclockwise, it's going to be positive. If you go clockwise, it's going to be negative. Now, if a rigid body is in equilibrium, neither its linear motion nor its rotational motion changes, which basically means that all your summation of your force in the x direction is going to equal to zero. All your summation and your forces in the y direction is going to equal to zero. And that means all your rotation, all your torques, which is your force times your distance, is going to equal to zero. So let's go ahead and look at an example. We get a woman whose weight is 530 newtons, is poised on a rigid end of a diving board with length 3.9 meters. The board has visible weight supported by fallocrium 1.4 meters away from the left end. Find the forces that the bolt and the fallocrium exist on the board. So let me go ahead and draw. So we got what, 3.9, 1.5. Let me go ahead and go over here. So we got a diving board. Diving board. So you got a bolt right over here. And you got a little fallopian right over here, little thing so you can jump. And you got a person going over here that's about to jump down. Now, let me go ahead and get those numbers. So what you got? You got length, the length for the weight. So that person has a weight going down there. And this is your weight length all the way to the bolt. 3.9 meters. And let me actually draw this in a different color. Now you got that little thing over here, the equilibrium. And that's going to be 1.4 meters away. So your equilibrium is going to issue a force that way. Let me It's the force of the equilibrium. And it is 1.4 meters away. So length for the it's going to call W is 1.4 meters away. And let's see. Now this weight over here is 530 newtons. What we're trying to find when the force of the bolt and the fulcrum exerts on the board. So we want to see all the forces on the board. So now, in order for it to be an equilibrium, that means all your torques is going to equal to zero. All right. Well, let's look at what's going to be. So all your torques is going to equal to. Well, let's look at the first one. Where's the first one's going? The first one's going downwards, which is going to be clockwise. So it's going to be negative. So your torque is going to, on the first one, it'll be your minus W times L for W, the length for that weight that we had, plus, I'm going to call this, I'm said F2, I'm just going to call it L2, F2. Just be easier. That way I would not have so many letters. Let's call this F2, L2. So this would be F2. Now F2 is going what? It's going counterclockwise. So it's going to be positive. So be F2, L2, plus, now you got a force on this one, and I'm going to call this F1. So let me just go ahead and say, let's say F1 going this way, let's say. So there's going to be F1, L1, 0. All right. Well, what's the length one from the bolt? Well, it's going to be 0. L1 is going to equal to 0. So this thing is going to go to 0, which means that the summation of all the torques is going to equal to minus W, LW plus F2, L2 is going to equal to 0, which means it's going to equal to minus 530 times 3.9 plus F2 times 1.4 is going to equal to 0, which means F2 is going to equal to 530 times 3.9 divided by 1.4. And if we add them all up, we should get 1,480 newtons. So this F2 is going to equal to 1,480 newtons. All right. Well, let's look at the summation of all the forces. Let me go ahead and do this one. Of all the forces in the y direction. What are we going to have? All right, well, let's look at the force in the y direction. Well, in the y directions, we're going to have F1 going down minus F1 plus F2 is going up. And then you got your weight, which is F3 going downwards. So it'd be minus F1 plus F2 minus your work. Your weight is going to equal to 0. And in this case, substituting the numbers, minus F1 plus we said F2 is going to equal to 1,480 plus 530, sorry, minus, negative. Is going to equal to 0, which means that F1 is going to equal to 1480 minus 530, and it's going to equal to 950 newtons. So we got the forces in the y direction. Okay, how about the forces in the x direction? All right. On this one, we don't have any force in the x direction. We just have the weight. This one is just affecting the y. It's not the axis. X-axis is the same thing, x. So all your force in the x direction is going to equal to 0, which means your F1 in the x-axis is going to equal to 0, your F2 in the x-axis is equal to 0, and your weight in the x-axis is going to equal to 0. Let's go ahead and check our work. All right, perfect. Now let's do one more example. You got the arm is horizontal of weight of 31 newtons. You got a muscle supply 1800 newtons of force. What is the weight of that heaviest dumbbell that he can hold? All right, let me go ahead and do this example 5. It's called example 5. So you got the weight of the dumbbell going down, the weight of the arm from the elbow going down, and then you get the muscle going up at a 13-degree angle. So let me go ahead and do this one. So here's the arm. I'm just gonna say this is the arm. And you got the weight of the dumbbell going down, the weight of the arm, and you got your muscle going in. I'm going to call M at an angle of 13 degrees. 13 degrees, 13-degree angle. Okay, and let me go ahead and label my knowns over here. So your arm weight is 31 newtons. Your mass is going to be, your total mass for that will be 1840 newtons. Your the length of the arm is 0.28. The length of the dumbbell is 0.62. And the length for the mass is going to be 0.15. Let me go ahead and label this. So this over here, that's your length for the dumbbell. This side over here, the length for the arm. And let me get different colors so we will not get confused. This over here, that's to be your length for the mass. Now, again, we need to have all our torques is going to equal to 0 in order to reach equilibrium, which is going to equal to, for the first one is going, again, it's going downwards. That means it's going clockwise. So it'll be minus WD times LD. Plus minus WA, LA, plus your mass times your L of M is going to equal to 0. All right, let's go. Which means that's your minus AWD, LD minus WA/LA plus MLM is going to equal to 0. All right, well, the first one. Let's go ahead and solve. So we already got the weight for the dumbbell. We got the weight for the dumbbell. Actually, we don't have the weight for the dumbbell. That's what we're looking for. Let's see. And in this case, we are looking for the weight of the dumbbell. That's what we are looking for. So WD, that's going to be our question mark over here. So we set up the equation. We don't have it, so we put 1 is WD times LD, which is going to be 0.62, minus the weight of the arm, which is 31, times the length of the arm, which is going to be 0.28, plus your mass is going to be 1840. Now, your length. What is the length that we actually have? All right. Well, let's take a look at this little fella over here. This is a convolution, and I'm going to say of m in the x direction vector, which we saw in chapter 2, and m in the y direction vector, where m in the x direction, let me get a different color, purple. Where we saw m in the x direction is going to be m cosine theta. Your m in the y direction be m sine theta. And in this case, our theta is 13 degrees. So in our example, we are moving in the y direction. We're not moving in the x direction. The muscle is moving in the y direction. So we're going to do m cosine m sine theta. And in this case, it'd be actually, let me just label them correctly. L of m, L of m, L of m, because we're talking about the length. The length for the m in the x direction, the length for the m in the y direction, the length of the m period, which is this one. So, and in this case, it's going to be your 1840 times sine 13 times your length in the mass, which is going to be your 0.15. It's going to equal to 0. So let me go ahead and write this down, all of it over in a neat sheet. So it'll be minus 0.62 W2, which is the first one, 0.328 times 31. So it'll be 8.68. So minus 8.68 plus 1840 times sine 13 degrees times 1.15. That's going to equal to 62.8087. 62.087. Okay, 0. Which means that minus 0.62 W2 plus 62.087 minus 8.68 will be 53.407. It's going to go to 0, which means that the weight of the dumbbell is going to equal to minus 53.407 divided by 0.62 negative. The negatives cancel out, and it's going to equal to 86.14 newtons. Wonderful. And if we looked at the forces in the y direction, what we get is going to be your minus weight of the dumbbell, because it's going down, minus your weight for the arm, plus your m sine theta, which is going to be your mass in the y direction going equal to 0, and your forces in the x direction, you're not going to have the dumbbell going in the x, just in the y going up and down. Same thing with the arm. So the only thing is you're going to have is in the mass, so be your mass cos sine theta is going to equal to 0, and this is going to be your m in the x direction. And that's what we just did. So our torques, you get, this is your first one, your dumbbell times your length for the dumbbell, your arm times your length for the arm, and then your muscle mass, glute muscle times the length for the glute muscle, which in this case, it's going to be in the y direction. So it'll be 30 sine theta. And we get 86.1. Perfect. Now, the next thing we're going to be talking about is called the center of gravity. Let me just go ahead and let me go define the center of gravity. So that brings us to the center of gravity. And this is where it is the point at which the weight can act when the torque due to the weight is being calculated, can be calculated. Usually, it's going to be in the dramatically center. It's going to be in the center of it. So, the center of gravity of a rigid body is the point at which the weight can be exerted to act when the torque due to the weight being calculated. And again, usually it's in the center of gravity is in the middle where the weight goes in. Now, your center of gravity is going to equal to your weight one. Your weight times your distance is divided by your weight. So let me go ahead and write that down. Now, your center X, center of gravity, is going to equal to your weight times your distance 1 plus your weight 2 times distance 2 plus etc. divided by your weight 1 plus your weight 2. So let's take a look at an example, shall we? So you got an arm composed of three parts: upper arm, 17 newtons, lower arm, 11 newtons. The hand is 4.2 newtons. Find the center of gravity of the arm. So let me go ahead and do that. So you got, right, let me go ahead and do this. So you got your weight one for your upper arm, your weight two, and your weight three. And the distances are, for the first one is 0.13, 0.38, and 0.61. 0.13, so here's a 0.38, and the last one, let me get a different color, and this one will be 0.61 meters. Now we need to calculate the center of gravity, much it is. And in this case, it's going to equal, again, your W1 x1 plus your W2 x2 plus your W3 x3 divided by your first weight, second weight, third weight. And in this case, it'd be 17. Well, how much are they, WC? 17, 11, and 4.2. Let me go ahead. So W1 equals 17 newtons, 11 newtons. And this one is going to be your 4.2 newtons. So it'll be 17 times 0.13 plus 11. Let me actually move this around a little bit so we'll have some more room to write. So that's 11 times 0.38 plus 4.2 times 0.61. Divide that out by the weights, which is going to be your 17 plus 11 plus your 4.2. And if you get that, according to my numbers, you should get 0.28. Now, what is the unit? We're talking about X. It's a distance, so it's going to have to be in meters. So what we're talking about in meters. So let's look around. So it'll be 0.28 meters. And that should conclude chapter 8, which talks about your torque and your center of gravity. If you have any questions, please email me at abunaemeh@gmail.com. Thank you.